Welcome, my name is Bernd Bischel. Welcome to our advanced machine learning lecture here. So in this chapter, we'll discuss how cost-sensitive learning works in machine learning, or at the very least, we'll give a basic introduction to the field. So here in this subpart, we'll figure out how we can define the cost-sensitive task. So we'll discuss what a cost matrix is, what misclassification costs are, and how they are specified through such a matrix. We'll discuss the minimum expected cost principle from a theoretical perspective, and then based on that, derive an optimal threshold for the binary classification problem with costs. And in the subsequent parts of this chapter, we'll then extend this, go more to practical algorithms, and really study how we can make ML algorithms respect these costs during training. Okay, but before we do this, let's start. What is cost-sensitive learning about? So cost-sensitive learning is, well, simply made for situations where we potentially have, well, I guess let's start by considering how classic classification tasks usually look like. So they're usually quite balanced. Usually we assume that errors have equal costs. And we now, in this setting here, we basically assume the opposite. So either we have some imbalanced setting where we usually care a bit more about the smaller classes, or we have explicitly been provided with specific misclassification costs. So how would these costs usually look like? So we would have something like a cost matrix down here. Yeah. So we would have the true label organized usually in the columns, and then we have the predicted label here organized in the rows, and then each cell entry would specify how these costs look like. And where do these applications occur? Well, I would actually argue that in many scenarios, these, assumptions for vanilla classification very often don't really hold. So very often either our tasks are imbalanced with unknown costs, and then I guess we have to talk about stuff like ROC analysis and ROC metrics, or we have explicitly been provided with such a cost matrix, or at the very least a rough approximation of such. And applications could come from medicine, so maybe we are being tasked with to diagnose whether a person is healthy or not. I don't know, maybe weather prediction, so we would incorrectly, or we would try to predict whether a certain, storm or hurricane occurs, and again, as in the medical case, you can pretty directly see that these negatives. So in this, for example, with the weather forecasting, so predicting that a storm does not occur and then it occurs comes with much higher costs than producing errors in the sense of false positives. So of course, it's not great to classify a person as having a certain disease when that person does not have that disease. But usually this implies that we run a more expensive, more detailed, subsequent form of analysis or inspection, and then hopefully we can correct our mistake. Sending somebody home under the assumption that that person is healthy when they are not, that's pretty bad. Not being able to predict such a certain crisis like a storm, that can be extremely bad. Or if we look into a credit granting, predicting that a person would pay back their credit when they actually default, so they cannot do that, and then we lose all of our money that we have granted to them. That's also obviously much worse than potentially declining a person and then losing the money we would make from us granting them the credit. I guess it's debatable whether in all of these situations there are concrete quantitative costs available to us. I guess especially in these medical situations. How do we put a price on, health or human life or something like that? In this lecture here, we will assume that these costs are usually somehow provided. I'll talk a little bit about how we could estimate them or how we can kind of technically produce them, but I will not really go into detail here, so I'll assume that they are there. If they are not there, then we are basically in this scenario of imbalanced learning with unknown costs, and then I would refer you to the parts of the lecture where we study this. So, for example, ROC metrics and so on. So how does such a cost matrix now look from a formal perspective? Well, I guess in a certain sense we already discussed that. Yeah, so we have these, we have this matrix here, basically looks like a confusion matrix. We have the true classes organized in the columns. We have the predictions organized in the rows. And then in each cell entry, we have the costs that that would occur if we would produce a certain classification on a certain scenario where we have a certain true label. So for example, here we would have we would be in the scenario of credit granting. And in this case, our client would pay back the credit, so they would not default. But we would predict that they would default. And in this case, we would lose some money by not making any money from that client. So we have these associated costs here. On the other hand, if they go broke, but we grant them the credit because we predict that they would not default, then we have much, much higher costs. And these individual costs or our estimates or approximations of these would be organized in these cell entries here of this cost matrix. So in formal notation, this would be CJK. Now the important thing is that the second part, the K, the second argument is going to be the true label, while the first argument, the J, is going to be the predicted label. Because the first one is the rows, the second one refers to the columns. Of course, you can also specify now simple 0-1 loss with this, so equal costs. Then, this would simply be a cost matrix. I don't know, let's maybe write this down for 3 classes, where we put a 0, so no costs, on the diagonal, because these are the cases where we classify everything correctly, and then we would put a 1 on all of the off-diagonal entries. This would be 0-1 cost, 0-1 loss. Guess we don't really need cost-sensitive learning for that, but it's nice to see that this is simply a special, can be seen as a special case of cost-sensitive learning. So, like I said, usually we are going to assume here that this matrix has been designed by experts. In cases where it's debatable how the specific entries of the cost matrix might look like, so we have to be aware of the following facts. So if the costs are too low, then often there is not enough change in a model. This can still occur then in costly errors that a model produces. And if our costs are too high, we might never predict these costly classes. So there is potential, element of filling around with these matrices. If there's kind of a certain, range of potential entries that make sense, and then we could run some form of a sensitivity analysis on that. Okay, so I have one slide where we can discuss a little bit how one could technically define these costs now in imbalanced scenarios where they are not available from domain knowledge. So a usual heuristic is to set these entries here. Let's maybe start with the second case. So if our true class K would be so we are in an imbalanced setting, so some classes are much, much larger than others, and usually the assumption is that the signal, the interesting stuff, happens in the smaller class. So for example, again, let's think about medical scenarios. Usually the smaller class are the persons who have potentially very rare disease. We want to predict that. Obviously, we now do not want to produce these false negatives. So predicting an observation as an element of the nority class, so predicting them, for example, as having the disease when they not have that, we see this as a less critical error. So we would normalize and fix all of these costs to 1. But predicting an element of a minority class, let me actually grab my pen here again, predicting an element of the minority class as an element of the majority class. So in this instance, predicting a sick person as being healthy, this is something that we want to penalize heavily through costs. And if these costs are not given, like I said, try to create them from domain knowledge. But if you need a technical handle, one common heuristic for this is simply counting the elements of the majority class nj and dividing them by the number of elements in the minority class nk. So if you want to define here the cost cj, k, this would be nj divided by nk. So for example, maybe our majority class has 1,000 elements. Our minority class would have, 100. then misclassifying in such a manner, so misclassifying as class J when we are actually in class K, in the majority class, would come with costs of 10. Okay? Here you can see this for the binary case where there's just two sizes, n minus, so the size of the negative class, which is kind of our default for that is usually that there's the larger one, the majority class, and here we have n plus as the costs, or sorry, the size of the positive class. And you can see here, kind of normalize this here to 1, and this is going to be a large value, and how large that is. So these are our false negatives that I talked about before, that we usually want to penalize in these cases, under the assumption that the positive class is the important class, where we don't want to misclassify anything here in this column. Then it depends now, of course, on this ratio here. So on the ratio between the sizes of the two classes. Okay, so is there a potential way of theoretically solving this problem? Yes, there is a simple, pretty direct way of approaching that, is assuming we have been provided with our cost matrix C, but that we would also have access to the true posterior distribution P given X. So, of course, we don't have that, we have to estimate that, but for a second, let's assume that we have been provided with that information. How would we then select our optimal class? Well, that seems to be pretty obvious, right? So we want to predict the class J with the smallest expected costs when we average out over all of our true classes. So on average, our prediction should come with the smallest costs possible for a given X, of course. So we are now kind of talking about how to create a base optimal or cost minimal prediction when we already know the posterior probabilities. So the only thing we'll now do here, this is pretty simple maths. So we'll just compute here the expected value when we integrate out over our true class. We'll just assume that this comes from this posterior distribution here, that from our true posterior distribution that we have access to. And then now we just compute this expected value because it's a finite number of classes. So in our case, this is always G. So we always compute here the probability that we are in class K. And then we multiply this with the costs that we are in class K when we predict class J. So J is an input here. So we do this for every J. So for one specific row here, our J would be fixed. Now we integrate out over all of these classes. And this would give us the average costs that we incur if we predict class K when we marginalize over the distribution of our true classes. Now, of course, we usually do not have access to this guy here, but we have to estimate that. I guess that's what classification and machine learning is all about. So if we would trust our probabilistic classifier, and if we have maybe validated this probabilistic classifier well enough, what we could do is simply plug in for this true posterior distribution our, again I'm losing the pen, our estimated posterior distribution from our classifier, and then we would apply the same formula. We'll talk a bit more about advanced principles later on, but if you would have a very, very well working system, you could directly turn its probabilistic output into cost optimal decisions. If you want to study this a little bit more in depth, there's a very well-known paper by Elkan, which is now about 20 years old, so the foundations of cost-sensitive learning, where all of this is discussed a bit more in depth. And what I should probably also say is that, usually what we did before was that we said, hey, if we look at this posterior distribution of a certain classifier, how do we transform this into a hard label prediction? Well, we take the most probable class, right? And we already said, well, if our classes are imbalanced and if we have certain preferences for certain classes, maybe this is not always the best. Here, this is also another case where the most probable class is not necessarily selected to be our cost optimal prediction. Okay, that depends now on the cost structure and on this probability distribution. It can actually be that I guess if that would not happen and we would always select the most probable class, we wouldn't even have to discuss this here. Yeah? But just to make you aware of that fact, it can actually happen that we would select a class which does not have the highest posterior probability, but which is cost optimal under this MECP principle here. Can we now also turn this into a direct computation of an optimal threshold, at the very least in the binary case? The answer is yes. So what I now want to do is I want to transform my, usually now, say, probabilistic classifier. We could also do this for score-based classifiers, which predict decision scores from -inf to +inf, but just to keep it a little bit easier here, I always refer now to this probabilistic case. So I have a binary classification task, I have a probabilistic classifier to make things simpler. Like I said, I'm assuming only to have two classes, and I want to figure out, is there a cost optimal threshold, so that everything that comes with a posterior probability above that threshold is classified as a positive class, and everything below that is classified as a negative class. And turns out this is very, very simple to compute from our given cost matrix, and we can end up with a very simple formula for this cost optimal threshold. Now, how do we do this? First of all, going to simplify our life even further by transforming our cost matrix a little bit. It turns out that, hopefully this is pretty obvious, that the optimal decisions based on our cost matrix do not change if we multiply our complete cost matrix with a positive constant. So if we double all of the costs overall, then our optimal decision does not change, because it only depends on the relative sizes of these costs. And also if we add certain constant shifts, or if we just add simple constant shifts to the matrix, again, this will not change our optimal decisions. And stuff like that is also discussed in the Alkan paper, but I hope that this is fairly obvious to us, and you believe this also without seeing a formal proof. Now, what we can do is we can scale and shift our given C matrix to get a simpler version C dash, and I just did that here. So what I want to do now is that for this column of the negative class, I want to transform this so that this column here becomes a 1, 0 column. How can I do that? Well, that's pretty easy. So the first thing, these first two entries here, these two entries in the first column, they will now change. In a certain sense, they are then the only thing that I don't know, care about or have to compute with. They're kind of only now, I've kind of now reduced the interesting elements of my 4-cell cost matrix to two numbers. So how can I do that? So the first thing I will do is I will subtract from every entry of my cost matrix, I hope I can mark this here, the C -1, -1 entry. So this would be this guy here, that was originally in my cost matrix C. I will subtract that from every entry, and that obviously makes this guy 0. And now you can see this also in the formulas here. So for the C dash, for this guy and for this guy, you can see that we always subtract this guy. Now for this first element here in the second column, where we have the 1, so originally we had here, let me see, originally we had here, we are in the negative class, but we would predict the positive one. Now, as I said, we are always subtracting from every entry now C -1, -1. So we have that in here. So what I now want to do is I want to transform this into a 1. So I'm now going to divide each entry in my cost matrix by this guy here. So, and this is exactly what you can see here, and hopefully this now explains our resulting structure of C dash. Okay, and of course, hope I don't have to say this, by using our MECP principle from before, we would now predict our class X as being positive when these costs here, these misclassification costs, are smaller than these here. So this now becomes extremely simple because we only have these two entries to compare. Okay, but what we can also do is we can now unroll our expected value for our misclassification costs and then use our C dash, plug that in, and from that get our hands on a formula for the optimal threshold. So how would that look like? So, well, maybe let's potentially go back to this guy here. So where does this come from? So, well, what are we doing here? We are now simply stating that we want the expected costs when we predict the positive class and marginalize over all of the other classes, or all of the classes, all of the true classes, which are just two because it's binary classification, these expected costs for our positive class should be smaller than the expected costs for our negative class. If that's true, we will predict, well, I guess the positive class, right? Because it has smaller expected costs. Now, we'll just write down our formula for this, and then plug in C dash. So how would that look like? So we have to now marginalize over our true classes. There are just two. So we have the case that we are in the negative class, and we now have to multiply this with the costs that we are in the negative class, but predict the positive one. We're here in this left case, right? So we now want to compute the expected costs for the positive class. So we could be in the negative class. This could be our true class, but we predict the positive one. Well, we then have to take the probability of being in the negative class times the costs of predicting the positive class when we are in the negative one. Plus, second case, we could be in the positive class, and now we take the probability of being in the positive class, and again now we take the cost of being in the positive class and also predicting being in the positive class. We do exactly the same thing here on the right hand side. So now we always consider the case that we predict, and maybe I should have marked it like that on the left hand side to be a little bit more to make it a little bit more obvious. So we always predict the negative class. Yeah? We now compute the expected costs for this prediction, and we now have to consider two cases, A being in the negative class and B being in the positive class. Okay? Now, if the left-hand side of this inequality is smaller than the right-hand side, we will predict the positive class. So how can we do that? We can now simply, first of all, I'm going to simplify this by removing a few of my notes. So we have now unrolled the expectation. The next thing we can do is we can figure out that this guy here, so this was C minus 1, comma minus 1 in C dash. So this guy here was 0, right? So because of our transformation. So I can remove that guy. You can see the only thing that was left on the right-hand side is this. And the left-hand side, well, we rearranged slightly. Well, the only thing we did here is we said for the probability of being in the negative class, we can also simply plug in the counter probability. So this is 1 minus being in the positive class. Well, and we did a second thing. This guy here, so C1 minus 1. So this guy, this is 1. So we can simplify this further, and then we end up here with this formula. And I guess the rest I will not read out now. So we can now simply bring our probability of being in the positive class to the left-hand side, and all of the remaining terms to the right-hand side. We can now plug in the definitions of our C dash based on the original cost matrix C. So simply these guys here, plug all of that in, simplify further, and then the thing that remains is that if our probability of our posterior probability is larger than this formula here, which is a simple calculation based on our original costs, then we will predict the positive class. So if you now compute this guy here from your cost matrix, this gives you the optimal threshold that you would use to make cost optimal predictions based on your cost matrix. So you can also write it down like that, in really compact form, to turn your probabilistic scores now into hard labels if you want to. And in the next section, we'll also study a bit more whether this always works, whether we should always trust that, and whether there's kind of a similar empirical approach that we could also try, which usually works a little bit better in practice. But this brings us to the end here.